Okay, I'm going to talk about a useful equation for working with buffers, and it is called Henderson-Hasselbach equation. It's only to be used when you have a weak acid and its conjugate base. So if you have HCl, you cannot use it. If you have sodium hydroxide, you cannot use it. You have to have, without a weak base, a weak acid, you cannot use it. It's the relationship between a weak acid's pKa and the pH of the solution that it is in. And it is derived from this equilibrium expression for the acid dissociation of a weak acid, the same one that I showed you before. When you have HA and it goes into water and it dissociates reversibly to this. That is the equilibrium expression you get. If you take the log of both sides, then you get this equation. And then if I move the log HA over to the left and the log of Ka over to the right, then I have this equation here. And we know that, and actually there should be a negative here, we know that negative the log of H is the same thing as pH, and we know negative the log of Ka is the same thing as pKa. So then our equation, this is the only thing on this page you really need to know, is the pH is equal to the pKa plus the log of the concentration of A minus divided by the concentration of HA. So what that says is if you know this pKa, and you can look that up in a table for any given weak acid, and you know the concentration of its two forms, then you know the pH of the solution, and that's really handy. And pH is important because, for example, enzymes function only in relatively limited pH ranges. We have 3 different enzymes here: pepsin, which is a protease that functions in the stomach; trypsin, which is another protease but functions in the pancreas; and lysozyme, an enzyme that hydrolyzes polysaccharides. And on these plots, we have on the x-axis pH for each one, and notice that their profiles are very different for each enzyme. Pepsin functions in the stomach. Well, the pH in the stomach is about 2, and so we need an enzyme that's going to reside in the stomach to have a lot of function at pH 2. And so the y-axis is relative enzyme activity, and pepsin has maximal activity at about pH 2. Trypsin looks like its maximum is at about 7, and lysozyme has a optimum of enzyme activity about pH 5. And notice how steeply it can drop off on either side of these pH maxima. Okay, and I alluded to this before. When we have a strong acid and we're looking at pHs of solution, we think about pH 7. We think about things like hydroxide concentration and H plus concentration. When you have a weak acid and its conjugate base, everything becomes centered on the pKa. So let's take this center case here. Let's say I have acetate or actually let's just do formic acid. This is formic acid. This is formate. Notice they differ only by the H plus. So this is the HA form. This is the A minus form. If I have significant quantities of both of these in solution, I have a buffer. And if I take this equation and I divide both sides by HA, then I wind up with HA divided by HA equals A minus divided by HA, right? Anytime I have an equation, I can do the same thing algebraically to both sides. Well, HA divided by HA is equal to 1, right? So that means that this ratio is equal to 1 when they're both the same concentration. And you may or may not remember, but the log of 1 is equal to 0. So that means in the case where I have equal concentrations of acid and weak base, then this part of the equation is equal to 0. And in that case, pH is equal to pKa, right? Because the log of A minus over HA is equal to 1, is equal to 0. Now, if I look at this case, right, so this is pH is equal to pKa. And that's the major take home there, that if you have equal amounts, the pH is exactly the same as the pKa, and that's actually one of the definitions of pKa. When A minus is in greater concentration than HA, I have more conjugate base than acid, we're going to see that the pH is going to be higher than the pKa. And so let's look at that. So if I rearrange this now, and I have A minus is over HA, that number is going to be greater than 1, right? And the log of something greater than 1, let's say take 10 for example, the log of 10 is equal to 1. So, and that is the log of my concentration of A minus over HA. And I've just given an example of being 10. It could be anything. But then if I take this value of 1 and plug it in up here, pH is equal to pKa plus 1. And I should actually look up the pKa for formic acid. Unfortunately, I can't pause my recording, but I think it's about, let's just say the pKa is about 2.3. So that means the pH of my solution is going to be 2.3 plus 1, or about 3.3. And the key to notice here is that the pH is greater than the pKa. Anytime you have more of the conjugate base than the weak acid, the pH is going to be greater than the pKa. Now we can't say what its relationship is to pH 7. We can only say what its relationship is relative to the pKa. And if you work through this for the case where you have more acid than base, weak acid than weak base, what you will find is that the pH will always be less than the pKa. So it's somewhat intuitive, because if you have more acid, it's gonna be more acidic than the pKa. And the analogy for this, just to provide an example, is let's say that the concentration of A minus over HA is now 0.1. Just for example, I've gone the opposite direction before. And anytime you take the log of something that's less than 1, the number is going to come out negative. And the log of this is -1. And so if I plug that into my Henderson-Hasselbach equation, then my pH comes out to be 2.3 minus 1, or 1.1. That's my pH. And notice that 1.1 is less than 2.3. And so the pH is less than the pKa. I'm going to stop there for now.